welcome back to the course. In the last class we were looking at how do we observe the NMR signal in the rotating frame. So, we introduced the rotating frame of concept which is shown here. You can see when we talk about rotating frame, what essentially we mean is that the RF frequency, the RF radiation which is applied is actually also rotating in the xy plane, and that is synchronized with the precession, the Larmor precession of the spin. So, when that happens we use the word resonance. So, in the rotating frame we are trying to reach a resonance condition such that the frequency or the rotational angular frequency of the B1, that is the magnetic field which is applied, is in synchrony with the spin. So, under such conditions in the rotating frame, so when you go into a virtual frame, a new frame of reference, the spin is now static because it is now having the same speed or same angular frequency as the magnetic field which is rotating in the xy plane. So, in such conditions the spin now starts precessing around B1, and this is again a Larmor frequency, Larmor precession which is happening now around B1, whereas in the previous case it was around B0 which was in the z direction. But we have removed that effect, we have removed the effect of the rotation around the z axis by going to a rotating frame where omega then becomes 0, and therefore, the only precession now which is noticeable in the rotating frame is this precession around B1, and this frequency is now given by omega 1 equal to gamma B1. So, this is for a given spin, but if you remember we looked at a collection of spins, we never look at a single spin, and if you look at a collection of spins, we represent this collection of spins by a net magnetization, or we call it as bulk magnetization vector. So, that is pointing in the positive z axis. So, now if you look at this spin, how it behaves, or this particular magnetization vector, how it behaves under an application of a magnetic field, we will see how that happens. So, in the similar situation we apply an RF radiation along the y axis, along this axis, and now the spin start precessing around the y axis. So, it is precessing or rotating in the z x plane. So, you see it is going from plus z, it goes to x, goes to minus z, minus x, and so on. So, this is how it keeps rotating in the rotating frame around the applied magnetic field which is B1. Now, B1 is actually an electromagnetic radiation, but it has electromagnetic radiation has electric component and a magnetic field component. So, we are now looking at only the magnetic field component, and the electric field component is ignored because we are looking at nuclear magnetic phenomena. So, only the magnetic field part of the electromagnetic radiation actually interacts with the spin. So, under this resonance condition, when this the omega naught, when the gamma equal to omega naught, gamma equal to omega equal to gamma B0, the resonance condition happens and the spin start precessing. So, this precession actually happens in, we can say this angle is called as 90 degrees, this all of us know, this is a perpendicular, and if you go further it is now 180 degrees. So, we can allow the spin to go by any angle we wish, and we can then stop the rotation. How do we stop the rotation? We stop the rotation by removing this B1. So, when we remove this B1, the spin is then frozen in the direction or in the angle to which it has come. So, we can go further, it will be 270 degrees, and if you go further it becomes 360 degrees. So, this is how basically NMR signal is observed. Each nuclei in a molecule will have its characteristic frequency depending on the chemical shift. So, we will look at the chemical shift concept shortly, but what basically it means is, suppose we have a molecule which has 3 hydrogens, 3 different types of hydrogens, each of the hydrogens will have its own omega value, that is own Larmor precession frequency, because each of them have a different rotational frequency. Now, therefore, we have to now excite all of them, means we have to have resonance for all of them at the same time. How do we achieve that? We achieve that by applying a pulse. So, this is where the pulse NMR concept comes into picture. So, how do we apply an RF radiation which is on resonance with all nuclei? So, remember on resonance can happen only for a particular value, but still we can apply a high frequency or a high power frequency such that all the spins are excited or in resonance. So, this is done using an RF pulse. An RF pulse is basically a short burst of RF frequency. So, you can see it is depicted here, it is an electromagnetic radiation of a very short duration. So, typically it is in the microsecond, and the amplitude, the height of this is the B1, which is what we discussed. The B1 is the RF magnetic field applied in the xy plane. So, this is applied in the x or y direction, and that is now a very short duration, and after some time it is switched off. So, as soon as you switch off the RF field, the radiation, the spin has rotated by some angle which we saw in the last slide, and that is the angle at which the spin stops, and that we call it as the flip angle, that is how much it has flipped. So, the RF frequency is applied at the center of the spectrum. So, this is something which was discussed in the previous course, how in the practical aspects how do we apply an RF pulse. We will not go into detail in this course. The main take home is the RF pulse, that is this pulse which shown here has 4 components associated with it. One is the width of the pulse, the duration, which is already shown here, which is typically in microseconds. Then you have the height or the amplitude of the pulse, which is the strength of the pulse, how strong is the pulse, that is represented by this notation by B1. Then you have 2 more parameters, one is the phase meaning it is applied along x axis or y axis, that is not shown here, but that is important. So, that is a third parameter, and the fourth parameter is the frequency of this. So, you can see this actually is having a frequency. So, what is the frequency at which this is applied, and that frequency is basically the Larmor, that is basically the resonance frequency. So, that is in megahertz. So, the frequency of an RF radiation is in megahertz regime, and that frequency is this shown here, but the strength is depending on how strong you want to excite the nucleus, how much or how long is the how much angle, flip angle you want to achieve. So, this is what, as I said, we apply in the center of the spectrum. So, let us say your molecule has nuclei or spins which are between 0 to 10 ppm, and this is the chemical shift scales which we will discuss again, as I said, shortly. And then you take the RF pulse is applied, you keep the frequency of the RF pulse somewhere around 5 ppm. So, what happens is it excites or causes resonance for nucleus on either side of 5 ppm. So, it will go on this side 5 ppm and this side 5 ppm. So, the center of the spectrum is what is usually chosen for applying the pulse. Now, let us look at this concept of pi by 2 and 180 degree pulse, which is very important when we go to 2D NMR. In a 1D NMR is simply applying a magnetic field, and you wait for some time, and after that time it has rotated by an angle by 90 degrees. At that moment we switch it off, the RF pulse is switched off. So, this is typically what is done in a 1D NMR, but sometimes we may have to go in a 2D and 3D NMR, we will have to go beyond 90 degrees. So, what is done is you apply the RF field, that is B1 perpendicular to in either y axis, or you can apply it along x and start with the magnetization which is along z axis. The magnetization flips by 90 degree, and you continue to apply, you do not stop the RF, let it be on. When you keep it on, it goes further and it keeps going, it can come up to 180. So, you can switch off at this stage. So, if you switch off at this stage, the signal is now, or the magnetization is now located at minus or say 180 degrees from the z axis, so minus z axis. So, that if you stop at that point, we say that we have applied a 180 degree pulse. This is a 90 degree pulse. So, we have applied the B1 as long as the magnetization has gone from z axis to x axis. Remember, it follows the right hand rule. So, it will go in the x z plane, and if you stop at 180 degrees, it is then called as a 180 degree pulse. So, this is the 2 basic pulses which are very important. You can also look at it from here, this is called an inversion pulse, because it is inverting, you can see it is here and it is just simply inverting a magnetization. I can also invert the magnetization from this direction, what you are seeing here, all the way to this direction minus x. So, when you go from a x axis to minus x, we use the word refocusing pulse. So, both are 180 degrees. So, refocusing pulse is also 180 degrees, inversion is also 180 degrees, but inversion is basically bringing magnetization from z to minus z, whereas refocusing is bringing from x to minus x or y to minus y. We will see this in more detail when you go to 2D NMR. So, this is now what happens after the pulse is stopped. So, this is what I shown here. So, what I said is we first apply a pulse which takes the magnetization, let us say by 90 degrees. So, this is a 90 degree pulse. Now, moment you remove the pulse, the magnetization has to go back to equilibrium. This is the equilibrium picture scenario. So, it has to go from this direction back to this. So, how does it go? It goes via 2 pathways, and those 2 pathways are called relaxation pathways. So, one is called T2 relaxation, which I will see now shortly, and the other one is T1. So, what is T2 and T1? So, T2 relaxation is basically the signal is signal has to come. Now what happens when you apply a pulse, the signals are all in phase, because you can see the magnetization have all come to the xy plane and they are all bunched along x axis. And now when they go back towards z axis, they have to again dephase in the xy plane, because that is the picture we saw in the classical picture in classical way. That has to happen, and that dephasing of the signal in the xy plane is called as T2 relaxation, and T1 relaxation is happening, which happens at the same time as T2, but it is a different pathway in which the signal builds up along the z axis. So, let us see a little bit more in detail these two relaxation pathways. So, this is shown here. So, we have brought the signal to the xy plane or x axis, the signals are all bunched together. Now, after removing the pulse, the signal is now free to go back to z axis. It has to go back to z axis because it has to reach the equilibrium situation. So, this is what happens, the spin starts now dephasing. This is basically they start spreading out in the xy plane, and then they spread out, and after some time they are completely dephased, completely meaning the spin vectors are all spread over this xy plane, and that basically happens slowly, and that process is T2 relaxation. So, T2 relaxation is nothing but the decreasing of the signal. Now, what happens is, now let us say we observe this, we keep a detector here. So, now we come to the detection part of this NMR signal. So, if I keep a detector along x axis, I will observe a maximum signal at this point when the signal has come to x axis, that is here shown in this plot, in this picture, in this point, that is at t equal to 0 time. When I start observing the signal, as soon as the B1 is switched off, I will get a maximum signal, but as soon as the relaxation begins, the signals are dephasing. So, if you see now, they are not all of them along the x axis, they are slowly going away. So, if you take a combination of all of this along the x axis, because remember detector is only here, it can only detect what is along the x axis. So, if you take a combination of this along x axis, it has now come down, it is not as good or as strong as the initial time. So, you can see this is shown here, it starts coming down, and then after some time the signal is also rotating, remember, because of the Larmor precession. So, it comes back again in this position, and that is shown here, it comes back, but it does not come back fully, it has reduced little bit because the dephasing is rephasing, that is, this is called dephasing, and rephasing is not complete, it has decreased a little bit, then again it dephases and so on. So, this dephasing is going on all the time, but at the same time there is an oscillation, this is a frequency happening, it is having a frequency at which it is oscillating, and this is nothing but the Larmor precession frequency. Okay. So, if the detector basically detects the signal going up and down with a particular frequency, and that frequency is nothing but the precessional frequency. So, that this signal which is detected is called a free induction decay. The reason we call it as a free induction is because the signal is free. Now, we have removed the pulse. So, the signal is free to go back to equilibrium, and the reason it is called induction, because the signal is detected by the magnets, these tiny magnets which are rotating, they induce a EMF in the coil which is kept along the x axis, and that causes the signal to be generated, and that is amplified and detected, that goes in a oscillating manner. So, this is induction. So, we are actually detecting the signal by induction, not directly, but indirectly through its induction in a coil. That is called and the decay, basically because the signal you can see is slowly going down and down, it does not come back fully, it goes down, and that is because of T2 relaxation. So, the signal in FID decays purely, essentially main component is T2 relaxation. So, this is how the signal is observed in NMR, and you can see that here the oscillation in the xy plane, as I said, is T2. Now, how, if you look at it, the FID which I showed in the previous slide, this one, this picture here, you can actually construct the same FID like this. You can think of a pure oscillation, because the signal is oscillating because of the Larmor precession, and that you multiply with a decaying part. This is T2 relaxation. So, if I multiply the T2 part, relaxation part, which is an exponential decay, into a simple oscillation which is cosine, I get the FID, that is what I showed in the previous slide. So, the FID is nothing but it consists of two components, as oscillation or a frequency component which is cosine or it can be sine, multiplied with an exponential decay term, and this is the total actually the FID which is detected, and there has to be a multiplicative constant here which we will see later, and that constant is basically this height which is at time t equal to 0, and that depends on the concentration or number of protons and so on. So, that factor also comes a third factor in this equation. So, now let us see what is the concept of chemical shift, because the frequency which I showed in the previous slide is each frequency, each proton in a molecule has a different frequency. So, which means it has to now depend on what is called the chemical shift. Why is the frequency is different? Because of this concept. So, what is the chemical shift? Let us look at this like this. So, this is the equation, the standard NMR equation without the sigma. So, just concentrate on this part, that is omega effective is gamma B 0. Now, what happens is each nucleus which is written as I here does not actually experience only B 0, it experiences a slightly reduced magnetic field or slightly increased depending on the sign of this term. So, therefore, what we do is we are now writing this term which represents an effective magnet or effective frequency of the nucleus. For example, let us say sigma is 0, then it becomes same as a standard nuclei, but if the sigma is not 0, then this is decreased, it is 1 minus this is less than 1, and therefore, this effective reduced frequency is present. So, this is essentially the concept of chemical shift, that chemical shift is essentially reducing the effect of the total magnetic field on the nucleus, and therefore, that results in the change in this angular frequency, and each nuclei, that is I, will have different angular frequencies depending on the value of this sigma I, and that is basically a very small value. This sigma I corresponds to roughly 10 to the power minus 6, and therefore, it is a very small number. So, it is just in a ppm scale this number. So, you can see it is not that it is changing this magnetic field by a lot, it is actually changing by a very small amount, and that therefore, with the word ppm comes into picture. So, now how do we calculate the ppm values, and that is what is the calculation which we will go into now. It says that when a frequency, the reference frequency, that is suppose say we go into a reference frame, a rotational frame of reference, that is what we saw rotating frame, there I can consider the rotational frame frequency as the standard frequency. So, what I have to do basically is now subtract this from this, because in my actual rotating frame the frequency experienced by the nucleus will be the rotating frame minus its frequency. So, remember again, if sigma is 0, then these two will cancel, because the omega r will become exactly equal to omega effective. In such a scenario, omega effective in the rotating frame will be 0, but not otherwise, in the sense if sigma is not 0, then this value is not equal to 0, and it results in this number which is gamma B 0 into sigma I. Hence, the FID is subtracted from the reference signal. So, this is what is standard is typically done for detection. We do not directly detect the signal as such, that is the FID as such. The FID is subtracted before digitization from the reference frequency, and reference frequency is nothing but the frequency, that is the megahertz rotating frame of reference, and the reference signal is detected and used for further analysis. Okay. So, that is basically how practically NMR signals are detected, and then we will see now look at example of how we can get multiple signals. So, this is again the picture of a free induction decay. So, you can see here the frequency of precession in rotating frame is now removed, because now this frequency what you are seeing is nothing but the difference between the reference signal and the effective signal frequency of the signal, and therefore, that is 0. This becomes 0 if they match exactly, but they may not match always, because they have a chemical shift value, and in such situation you will have this oscillation. So, what is done next is that you Fourier transform this FID. So, this FID is digitized, remember this concept, you have to digitize the FID and subject it to Fourier transform, and that gives us finally the NMR spectrum. So, the technique of Fourier transform is something again we will not be able to go in detail. What Fourier transform is a mathematical approach. What it does is it takes a signal which is varying with time, and it then gives out the frequency components present in that signal. So, if there is a one particular signal on present, it will give you one peak. If there are many signals, it will give you many peaks. So, that is what we will see now if you have multiple signals. So, this is what is shown here, that Fourier transform basically takes any signal which varies with time. So, this is the signal, let us say an arbitrary signal which is detected by NMR, because let us say we have 2 cosine waves. So, we may have 2 signals, let us say 2 protons in my molecule. In such scenarios, for example, let us say methanol, if you are looking at a molecule such as methanol, you will have 2 frequencies CH3 and OH. So, you have 2 frequencies present. So, FID will be a combination of those 2, because remember the detector does not care how many frequencies are present, it simply adds the 2 FIDs and then that is what looks like this. But this actually may be a component, there are 2 components present here, one could be a low frequency and one could be a high frequency. Not only that, the amplitudes are also may be different. For example, in a CH3 of methanol, it has 3 times stronger than a CHOH of methanol, which is only 1 proton. So, you see the amplitude also can vary, the frequency also will vary. So, this is how we can decompose or we can separate the frequencies into 2 components. And now, if I do a Fourier transform of this signal, remember I do not know these frequencies, I only have this in my hand, that is what is detected and stored in the computer, and only that can be used for Fourier transform after digitization. Remember, this is a digitized signal, although it is shown as a continuous signal, it is not really a continuous signal, it is a digital signal, means it is discrete values at every point, there are the number of points here and then the signal is taken at those points. So, if you take a discretized signal and you then subject it to Fourier transform, it will give me 2 frequencies, because there are 2 frequencies present as per this picture here. Now, if you look at this, this is one comes at the frequency which is the frequency of this particular signal, and other frequency, the peak at other frequency is this signal. And now, the height of the peak of this particular peak depends on this amplitude here. So, if this amplitude is 3 times this or 2 times that, it will now depend on that ratio. So, you see the amplitude also the NMR Fourier transform also tells us the amplitudes, relative amplitudes of the signals, and this relative amplitude is something which is unique to NMR spectroscopy, because it gives us a way to quantify the signals, and this is that one of the unique properties of NMR which we listed in the previous classes, where you can see that is what is used in several of the applications. So, let us say that if you have 3 signals, so this is in this particular case I have taken example of ethanol. So, in ethanol you have OH, CH2 and CH3. This is again I am just giving another example of how Fourier transform works, how NMR signals come out. So, you can see there are 3 signals. So, this is one particular frequency corresponding to CH3, a second frequency corresponding to CH2 and third corresponding to OH, and all of these signals are coming together from the sample. So, the detector cannot distinguish between these individual signals, and all of them come together and each of them now has this form. Each of them is a FID, individual FIDs, but the FIDs are added together to give the signal. So, this one has a T2 relaxation of its own, this will have a different T2, this will have a different T2, and when we do a Fourier, when we combine the signals, we will get 3 different terms which are added together. So, this is a combined FID or observed FID, which is simple linear addition of A plus B plus C. So, one thing again which is missed out here and you should keep in mind is amplitude. So, you see here this is CH3, so it will be 3 times stronger, so it will be 3 times higher in amplitude compared to this is 2 times and this is 1. So, this will be 3 times, this term will have a factor 3 here, this term will have a factor 2 here, this term will have a factor 1 here. So, that is how if you do a Fourier transform of this signal, which is a combined FID which is detected at the detector, we will end up getting 3 signals, and these 3 signals now corresponds to each of these, and one of them, as I said, omega CH3 is shown 3 times stronger compared to CH2 and compared to OH. So, one thing you will notice in this spectrum, so this is the NMR spectrum which is the display which is shown here, and this is what is displayed in NMR spectrometers. The peak is not anymore a single line which was shown in the previous slide, it has a width, you can see there is a width to this line, this has also a width. So, what we do is we do not simply take the height of the peak, when we calculate the number of protons we take the area. So, the area of the peak is actually considered for calculation, and the area of the peak relatively depends on the number of protons. So, if you take the area of this peak, it will be 3 times the area of this peak, and this peak will be 2 times the area of this peak. So, if you take the relative areas, it is 3:2:1. So, again remember NMR gives us the relative number of protons and relative number of relative quantification. If you need absolute quantification, if you want to know the exact concentration of ethanol in your sample, that will not be possible by simply taking a spectrum like this. For that you will have to use a reference compound of known concentration, and that known concentration area which you will calculate will then decide, will tell you how much is the concentration of the molecule of your interest. That is how we calculate the absolute concentrations. So, this is how basically NMR signals are detected. In the next class we will look at one dimensional spectrum and look at more parameters such as chemical shifts and spin-spin coupling.